Hello there, and welcome to the Sleepy Space Channel. 3 out of every 4 stars in this galaxy are red dwarfs, and not one red dwarf anywhere in the sky is bright enough for a human eye to see. Within 17 light-years of the Earth, there are roughly 60 stars, and you will only ever see 9 of them. The rest are not distant. They are simply below the floor of human vision, and always have been. Among them are stars that erupt several times a year, 4 dead ones holding a sun's mass inside an Earth's volume, 2 that never quite caught fire, and 1 beloved world that never existed at all. Tonight we survey all 60. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. The sky above you is exactly as it has always been. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. The nearest 60. Within about 17 light-years of the Earth, there are roughly 60 stars. That figure is not a poetic estimate. It is a working census, assembled over the last 2 centuries and revised whenever something faint enough is finally noticed. 60 suns, scattered through the dark in every direction around this planet, each one burning steadily and independently, each one holding its own gravity and its own family of whatever material happened to gather there. Some are older than our own star by billions of years. A few carry worlds. All of them are close enough, in the arithmetic of the galaxy, to be called neighbours. Out of those 60, a person standing outside on the clearest night of the year, under a sky with no city anywhere near it, will be able to see 9. That number moves a little depending on where you stand on the Earth, how dark the sky above you is, and how good your eyes happen to be. Call it 9 as a reasonable reckoning. The rest, the other 50-odd, are not merely difficult to make out. They are entirely absent from human vision. No amount of patience helps. No amount of dark adaptation helps. They are below the floor of what an unaided eye can register, and they always have been. This is worth sitting with before anything else is said, because it is the fact the rest of this survey turns on. The nearest 50 stars to our own are invisible to us. They have been there the entire time. Every generation of people who has ever looked up, every navigator, every calendar maker, every child taught the names of the constellations, has been looking at a sky in which the overwhelming majority of the nearby population simply does not appear. It would be easier to accept if the sky looked empty. It does not. From a genuinely dark sight, the sky is crowded almost past counting, with something on the order of 5,000 stars visible across the whole celestial sphere. The crowding is real. What the crowding is made of is the surprise. Almost none of those 5,000 are anywhere near us. The median distance to a naked eye star runs into the hundreds of light-years, and many of the brightest run into the thousands. The visible sky is a catalogue of the distant and the unusual. Our actual neighbours are almost entirely missing from it. Consider what the census looks like when you order it properly, by distance rather than by brightness, and the shape of the problem becomes clear immediately. The nearest system to the Sun sits at about 4¼ light-years. It contains 3 stars. 2 of them are bright, warm, and reasonably similar to our own, and from the southern half of the Earth, they appear together as a single brilliant point low in the sky. The third member, and the one that is actually closest to us, is a small red star that no human eye has ever seen. It is roughly 100 times too faint. The nearest star in existence is invisible from Earth, and it will remain so. The second nearest system, at just under 6 light-years, is a single red star, older than our own by several billion years, and also invisible. The third nearest system, at about 6.5 light-years, is a pair of objects that are not quite stars at all. They are invisible, and more than that, they were unknown. Nobody on Earth had any idea they existed until a little over a decade ago. The fourth, at about 7.5 light-years, is a solitary object colder at its surface than the freezing point of water. It too was found within the last dozen years, and it too is invisible. Only at the fifth position does the census finally produce something the eye can find. At about 8.5 light-years, there is a hot white star that is, as it happens, the brightest star in the entire night sky. Every human being who has ever lived has seen it. It has been used to mark the seasons, to time the flooding of rivers, and to steer ships. And even that star, the most visible object in the census, is carrying something invisible with it, which we will come to in due course. So the pattern is set from the first few entries. 4 of the 5 nearest systems to the Sun are entirely beyond human sight, and 2 of those 4 were completely unknown within living memory. There is a temptation, hearing this, to assume it must be a matter of distance. It is not. Distance is the smaller part of the explanation, and the larger part is stranger and considerably less comfortable. It has to do with the enormous range across which stars vary in brightness, and with the fact that the eye is a detector with a hard limit. Those 2 facts working together produce a sky that is sorted almost entirely by luminosity, and almost not at all by nearness. We will build that argument properly, piece by piece, because it deserves to be understood rather than simply asserted. For now, it is enough to note the outcome. What we call the night sky is not a map of our surroundings. It is a map of the loudest objects in a volume tens of millions of times larger than our surroundings. The nearby population is quiet, and the quiet ones do not appear. It is also worth saying plainly that this arrangement is temporary. None of these 60 stars is fixed. They are all moving, and so is the Sun, and the whole local group of them is drifting around the center of the galaxy at something like 230 kilometers per second, taking roughly 230 million years to complete a single circuit. Relative to one another, the motions are gentler, a few tens of kilometers per second, which is why the neighborhood holds its rough shape across a human lifetime. But over tens of thousands of years, the ordering changes. The nearest star tonight will not be the nearest star then. The census is a snapshot of a slow current. These 60 are not a family. They did not form together, and they are not bound to one another. They are simply the objects that happen to be passing through this region of the galactic disk at the same time we are. In another few million years, the list will be substantially different, and nothing in particular will have happened. The region itself has a history worth knowing. The Sun sits inside a cavity in the interstellar gas, roughly 1,000 light-years across, carved out by ancient supernovae and filled now with hot, extremely thin material. Because of that cavity, the local density of stars is a little below the average for the galactic disk. There are about 4/1000ths of a star per cubic light-year here. A sphere 17 light-years in radius holds about 20,600 cubic light-years of space, which is precisely where the figure of 60 comes from. It is not a coincidence, and it is not a special number. It is simply what that volume of this part of the galaxy contains. What that volume contains, however, turns out to be considerably stranger than a list of 60 ordinary suns. Among the 50 or so invisible members, there are stars that erupt without warning, and by factors our own sun has never approached in all of recorded history, throwing enough radiation at their nearest worlds to strip an atmosphere of its protective chemistry within a few years. There are objects that gathered themselves out of the cold, reached toward fusion and never quite managed it, and which have been cooling in the dark ever since. There are stars that were catalogued only in the last 20 years, despite sitting closer to us than objects known for centuries. And there are 4 bodies in the local census that are not living stars at all, but the collapsed remains of stars that finished burning long ago, each one holding roughly the mass of the Sun inside a sphere no larger than the Earth. That last group deserves the arithmetic spelled out, because it is the point at which the whole picture turns cold. 9 stars visible to the eye. 4 dead ones hidden among the rest. Roughly 1 stellar corpse for every 2 living stars a person will ever be able to see from their own back garden. None of that is a matter of interpretation. It is what the census says. Before any of it can be examined properly, though, there is a prior question, and it went unanswered for almost the whole of human history. Nobody could say how far away any of these objects were. Without distance, none of the rest of it means anything at all. A point of light in the sky carries no label. It could be a small lamp close by, or a furnace unimaginably far off, and for thousands of years, there was no way whatsoever to tell the difference. That problem, and the strange, patient, almost absurd way it was finally solved, is where the survey properly begins. Part 2. The first honest measurement. For nearly the whole of human history, nobody knew how far away a single star was. Not approximately. Not within a factor of 1,000. The question was open, and there was no method that could close it. The difficulty is easy to state, and was extremely hard to solve. Brightness alone tells you nothing. A faint point of light might be a small, cool star sitting relatively close by, or it might be a furnace of enormous output at a distance no one had a word for. Both produce the same appearance. Without some independent handle on distance, the sky is a flat surface with lights painted on it, and for thousands of years, that is essentially what it was treated as. There is only one direct way to measure the distance to a star, and it relies on the Earth's own motion. As this planet swings around the Sun, our viewpoint shifts. Over 6 months, it moves across a baseline of 2 astronomical units, roughly 300 million kilometers. A nearby star, viewed from opposite ends of that baseline, should appear to shift very slightly against the far more distant stars behind it. Measure the shift, know the baseline, and simple geometry gives you the distance. The method is called parallax, and in principle, it is straightforward. In practice, the shifts are so small that they defeated every attempt for centuries. The largest stellar parallax in the entire sky, belonging to the nearest system, is about 3/4 of an arcsecond. An arcsecond is 1/3600th of a degree. 3/4 of one is roughly the angle a small coin makes when you look at it from 5 kilometers away. That is the biggest such shift available anywhere. Every other star in the sky produces something smaller, and most produce something very much smaller. There is an irony buried in this that took a long time to unwind. In the centuries when the question of whether the Earth actually moved was still being argued, the absence of any visible stellar parallax was used as evidence that it did not. The reasoning was sound. If the Earth truly swung around the Sun, the nearby stars should shift, and they stubbornly refused to. The flaw was not in the logic. The flaw was that nobody was prepared to believe how far away the stars really were. The absence of a detectable shift was itself a measurement, and what it measured was a distance beyond anything anyone had been willing to imagine. The first successful measurement, made a little under 2 centuries ago, is one of the more instructive stories in the history of the subject, mostly because of the target that was chosen. It was not a bright star. It was a dim and thoroughly unremarkable double in a northern constellation, a pair that nobody had any particular reason to care about. It was chosen for one reason only. It moved. Across years of observation, it drifted measurably against the background of the sky, and that drift was taken as a hint that it might be close. The reasoning was indirect but sound, and it turned out to be correct. The star sits at about 11 light-years. That heuristic, that the fastest-moving stars are probably the nearest ones, went on to become the single most productive tool in the search for nearby objects, and it stayed productive for the next century and a half. It is worth holding on to because almost every late arrival in this census was found by motion rather than by light. The measurement itself took well over a year of patient work, night after night, on an instrument built by one of the finest lens makers then alive. Most nights, the star barely moved at all. Slowly, out of accumulated noise, a number emerged. For the first time in the history of the species, a human being knew, in real and defensible units, how far it was to another sun. There is a quiet second story folded in beside it. Far to the south, an astronomer had already measured the distance to the nearest system several years earlier and had arrived at essentially the right answer. He did not trust it. He checked and rechecked and doubted and delayed, and by the time he finally published, he had been beaten into print by a matter of weeks. The first map of the neighborhood very nearly belonged to him, and he lost it to his own caution. The reaction at the time captured the moment well. It was said that the sounding line let down into the ocean of stars had at last touched bottom. For thousands of years there had been no way to measure the depth of the sky at all. Now the line had gone down, and finally struck something. With distance available, the units of the subject fall into place, and they are worth stating carefully, because everything that follows depends on them. The base ruler is our own star. Light leaving the sun reaches the Earth in about 8 minutes and 20 seconds. That distance, roughly 150 million kilometers, is called an astronomical unit. It is the natural measure of a planetary system, and it is the last distance in this entire subject that anyone measures in minutes. Beyond that, everything is measured in years of light. 1 light-year is about 9.5 trillion kilometers, which is about 63,241 astronomical units. The nearest star, at 4.25 light-years, sits at roughly 268,000 astronomical units from here. Hold those two numbers next to each other, because the ratio between them is the real shape of the local volume. Our entire planetary system, out to the orbits of the ice giants, spans a few tens of astronomical units. The gap to the next star is more than 250,000. The jump is not incremental. It is a change of category. There is a smaller model that makes it easier to hold. Shrink the sun to a grain of sand, 1 millimeter across. On that scale, the Earth is a speck of dust about 10 centimeters away, and the whole planetary system spans about 10 meters end to end. The nearest star, on that same scale, is 30 kilometers distant. Between the grain of sand and the next grain of sand, there is nothing but 30 kilometers of empty air. Astronomers use one further unit that comes directly from the parallax method. A star showing a parallax of exactly 1 arcsecond sits at a distance of 1 parsec, which is about 3.25 light-years. No star is that close. The nearest is at roughly 1.33 parsecs, which is why its parallax is 3/4 of an arcsecond rather than a whole one. 2 other measurements complete the picture of how a star moves, and untangling them from one another is a large part of the work. Parallax is an annual back and forth, a small ellipse traced out once a year as the Earth returns to where it started. Proper motion is a steady drift in one direction that never reverses. In raw data, the two are superimposed, and separating them takes years of observation on the same object. The third component, motion directly toward us or away from us, cannot be seen as movement at all. It has to be read from the shift of lines in the star's spectrum, and it is the only one of the three that reveals itself in a single night. There is one further number that makes the whole selection effect visible at a glance, and it is called absolute magnitude. It is simply the brightness a star would appear to have if it were placed at a standard distance of about 32.5 light-years. Once you have that figure, apparent brightness stops being mysterious. Distance dims a star according to an inverse square, so doubling the distance cuts the light to a quarter. Across the range from 4 light-years out to 4,000, that is a factor of 1,000,000. It sounds like an enormous effect, and it is. It is also far too small to matter, because the intrinsic luminosity of stars spans a range of more than 100 million to 1. The dimmest stars and the most luminous ones differ by so much more than distance ever does, that distance is very nearly beside the point. What took a lifetime of nights to accomplish once is now routine. A single space observatory has measured parallaxes for well over 1 billion stars, at precisions expressed in millionths of an arcsecond. The technique that could barely reach 11 light-years now reaches most of the way across the galaxy. And yet the local census is still not closed, and the reason is worth stating clearly because it explains almost every late arrival in this survey. Parallax only works on objects you have already noticed. It is a measurement you perform on something that is already in your catalogue. An object that emits almost nothing in visible light never enters a visible light survey in the first place, so it never becomes a candidate for having its distance measured at all. It is not that such objects were measured and found to be far away. They were never measured because they were never seen. That gap is where roughly 50 of our 60 nearest neighbours have been sitting the whole time. And the first of them, the very nearest star in existence, is where the survey turns next. Part 3. The nearest star in existence. At 4.25 light-years, there is a small red star. There is nothing closer. In the whole of the observable universe, no other sun sits nearer to this planet than that one, and none ever has within the span of human history. It is about magnitude 11. The unaided human eye reaches roughly magnitude 6 under an excellent sky, and each step of 1 magnitude is a factor of about 2.5 in brightness. 5 magnitudes is a factor of 100. So the nearest star to the Earth is about 100 times fainter than the faintest thing a person can see. It requires a telescope. It has always required a telescope. Not one human being in the entire history of the species has looked up and seen it. Its physical properties explain why, and they are worth going through slowly, because this star is the most representative object in the entire local census. It is not an oddity. It is the type specimen for the majority. It carries about 12% of the Sun's mass and about 15% of its radius. In size, it is comparable to a large gas giant, though it holds hundreds of times more material in that same volume. Its surface sits near 3000 Kelvin, against our own star's 5800. That temperature difference is what makes it red, and it is also what makes it faint. The total energy it radiates is about 1 part in 600 of the Sun's output. But the number that matters for visibility is worse than that, because a cool star does not distribute its energy the way a hot one does. Most of what this star emits comes out in the infrared at wavelengths around a micron, which is entirely beyond the range of human vision. In visible light alone, the deficit is closer to 1 part in 20,000. The star is producing a respectable amount of energy. It is simply not producing it in the narrow band our eyes were built to receive. The relationship between a star's mass and its output is steeper than most people expect, and it is the reason the deficit is so severe. Luminosity does not scale with mass in any simple proportion. For stars in this range, it rises roughly as the 3rd or 4th power of the mass, so a factor of 8 in material becomes a factor of several hundred in light. The star has an 1/8 of our own star's mass. It produces about a 600th of the energy. Nothing has gone wrong. That is simply how the physics runs. The underlying reason sits in the core. Less mass means less weight pressing inward, which means lower central pressure and a lower central temperature. Fusion is exquisitely sensitive to temperature, so a modest reduction at the center translates into an enormous reduction in the rate at which hydrogen is converted. The star burns slowly because it is not being squeezed hard. Its faintness and its extraordinary lifespan are not two separate properties. They are the same fact, seen from two directions. It is also worth noting how close this star came to not being a star at all. The minimum mass required to sustain hydrogen fusion is about 7.5 to 8% of the Sun's. This one sits at about 12. It cleared the threshold, but not by a wide margin. A slightly smaller cloud of gas at the same location would have produced something that glowed for a while on gravitational contraction and then began cooling forever, and we would be describing a very different nearest object. It was found, when it was finally found a little over a century ago, in exactly the way most of this census has been found. Not by its light, which is negligible, but by its motion. It shifted position on photographic plates taken from a southern observatory, and that shift marked it as something close. Its interior is arranged differently from ours as well. Below about 35% of the Sun's mass, a star can no longer maintain a separate radiative zone around its core. The entire body becomes convective, churning from the center all the way to the surface in a single circulation. This star is well below that threshold, so it churns throughout. That single structural fact has two consequences, and they pull in opposite directions. The first is longevity. Because the whole star mixes, it is not restricted to burning only the hydrogen that happens to sit in its core. Fresh fuel is continuously carried down and spent material carried up, so the star can eventually consume nearly all of its hydrogen rather than the small central fraction our own Sun will manage. Combine that with a fusion rate so slow it barely registers, and the result is a lifespan measured in trillions of years. Our star has perhaps 5 billion years of ordinary burning left. This one has something on the order of 4 trillion. That is a large enough number that it changes what the sky means. Every red star of this kind that has ever formed anywhere in the universe since the very first ones is still burning right now. Not one has ever reached the end of its life. They are all still in their opening chapter, and they will still be burning long after every star like our own has collapsed into a cinder. The second consequence of that churning is less benign, and it is the subject of the next part of this survey. A fully convective star generates its magnetic field differently from a layered one, and the field it produces is not gentle. The average surface field strength on this star runs to hundreds of Gauss, hundreds of times our own star's average. Its rotation is slow, about 90 days against our star's 25, and on a Sun-like star, that slowness would imply magnetic quiet. On a fully convective star, it implies nothing of the kind. There is a magnetic activity cycle of roughly 7 years, loosely analogous to the 11-year cycle we are used to, but far less regular and considerably more violent at its peak. Its X-ray output, from a body a fraction of the Sun's size, is broadly comparable to our own stars in absolute terms, which is an extraordinary ratio when you account for the difference in surface area. There is one more piece of its situation to establish, and it concerns where it sits. This star is not entirely alone. It is bound, though only barely, to the two brighter stars in the same system. It orbits them at a distance of roughly 13,000 astronomical units, taking something on the order of 500,000 years to complete a single circuit. That orbital radius deserves a moment. 13,000 astronomical units is more than 300 times the width of our own planetary system out to the ice giants. The nearest star's orbit around its own companions is a structure so large that our entire solar system would be a detail inside it. The binding is marginal enough that it may not be permanent, and there is a reasonable argument that this star was not originally part of that system at all, and may not remain part of it indefinitely. At those separations, gravity holds on very lightly. There is a question that tends to arrive at exactly this point, and it is worth answering directly and then setting aside. Could anything ever cross that gap? The honest answer is that our fastest machines, the probes already traveling beyond the edge of the Sun's influence, would need something on the order of 75,000 years to reach this star. There have been serious proposals for doing better, including one well-funded program that imagined a fleet of very small probes driven outward on a beam of laser light. That program has quietly gone dormant, never formally cancelled, most of its promised money never spent. The crossing is a subject deep enough to deserve its own night, and it has already had one. This survey is not attempting the journey. It is reading the map. What the map says about this particular star is the thing worth carrying forward. It is the closest object of its kind to the Earth in all of existence. It has been burning at that spot through every year of human history, through every civilization that has ever raised a monument to the sky, and through every set of eyes that has ever turned upward on a clear night. It was unknown until the 20th century. It was not hidden behind anything. It was simply too faint to notice. And it is not a calm neighbour. Part 4. The star that sets itself alight. Our own sun is, by the standards of the local census, remarkably boring. It varies in output by about 0.1% across its 11-year cycle. It produces flares, and the largest of them can disrupt radio communication and push aurorae toward the equator, but in terms of the star's total output, they are a rounding error. The sun's defining characteristic, from the point of view of anything living underneath it, is constancy. The nearest star has no such characteristic. It is what astronomers call a flare star, and the behavior that earns it, that description has no real solar equivalent. One recorded event brightened it by a factor of roughly 14,000 in the far ultraviolet. Not over hours, over seconds. The whole event rose and faded in about 7 seconds, and it was caught simultaneously by 5 separate observatories working at different wavelengths, which is the only reason its full extent is known at all. A factor of 14,000 is not an unusual solar flare scaled up. It is a different category of event. Nor was it an isolated accident. Outbursts of that class occur on that star at least 5 times a year. They are not a malfunction or an anomaly. They are part of how the star ordinarily behaves, and they have presumably been happening at some comparable rate for billions of years. There is one event in particular that puts the whole survey in an odd light. On one occasion, the star brightened in visible wavelengths by a factor of nearly 70. For a few minutes, the nearest star to the Earth, the star that no human eye has ever seen, would have been faintly visible to an unaided observer who happened to be looking at exactly the right patch of southern sky at exactly the right moment. The most invisible object in the neighborhood briefly became visible by setting part of itself on fire. The mechanism behind this is understood in outline. In a fully convective star, the churning interior drags magnetic field lines with it and tangles them. Tangled field lines store energy in much the same way a twisted band stores energy. When the geometry becomes unstable enough, the lines snap into a simpler arrangement and release that stored energy all at once, dumping it into the overlying plasma as radiation and as a flood of accelerated particles. The same process runs on our own sun. The difference is one of scale relative to the star and of frequency. This is not a peculiarity of one star, which is part of why it matters for the census as a whole. Roughly a third of the red stars in the most common class show flare activity detectable from Earth, and among the coolest and the youngest of them, that fraction rises steeply. The most energetic outbursts recorded on nearby red stars release something on the order of 1,000 times the energy of the largest solar flares ever observed. Flaring does decline with age, as a star spins down and its magnetic dynamo weakens. But for stars of this kind, the spin-down runs on a timescale of billions of years, so the violent phase is not a brief adolescence. It is most of the star's very long life. The character of the light released is what does the damage. Flare emission is heavily weighted toward the ultraviolet and the X-ray, which is precisely the portion of the spectrum that breaks apart atmospheric molecules and damages the chemistry of anything living. A flare that raises a star's visible output by a factor of 70 may raise its ultraviolet output by a factor of thousands. The eye would register a brief flicker. An atmosphere would register something considerably worse. Why this matters so much more here than at home comes down to a single geometric fact, and it is the hinge of the entire argument. A dim star has a habitable zone drawn tightly around it. If a planet is going to receive enough energy for liquid water to survive on its surface, and the star produces only a 600th of the sun's output, then the planet has to orbit extremely close. In this system, that region sits at something like 3 to 800ths of an astronomical unit. Our own innermost planet orbits at nearly 4/10. The temperate region around the nearest star lies well inside where our own system's innermost world sits. Now put a flare into that geometry. An outburst that would be an interesting curiosity at 1 astronomical unit is, at 500ths of 1, delivered with 400 times the intensity. Proximity is not a small correction here. It is the whole story. The consequences have been modeled in some detail, and they are sobering. For an atmosphere resembling Earth's, subjected to that flare regime, the models suggest ozone depletion approaching 90% over about 5 years of repeated events. The critical part is not the depletion figure by itself. It is that the recovery time is longer than the interval between outbursts. The atmosphere never gets the chance to rebuild what it lost before the next event arrives. With the ozone gone, ultraviolet reaches the ground unfiltered. During one of these outbursts, the surface dose could run to something on the order of 100 times the level that kills the most radiation-resistant organism known on Earth. That organism survives doses thousands of times what would kill a human being. It is the standard by which biological toughness is measured, and it is being exceeded by 2 orders of magnitude. Radiation is only half of the problem. The particles matter as much as the light. Coronal mass ejections from a star of this kind can deliver stellar wind pressures thousands of times what the Earth experiences from the Sun. That is enough to compress a planetary magnetosphere severely, and if the field is weak, enough to push past it entirely and reach the upper atmosphere directly. Over hundreds of millions of years, that kind of repeated stripping removes an atmosphere piece by piece and does not give it back. And there is an earlier problem that arrives before any of this, during a phase most descriptions skip over. A star of this mass does not settle into its steady burning quickly. It spends up to 1 billion years contracting toward the main sequence, and during that contraction, it is substantially brighter and hotter than it will eventually become. Any planet sitting in what will one day be the temperate zone spends its first 1 billion years being cooked by a star that has not yet calmed down. Whatever water it started with may well have been driven off before the star ever reached its adult brightness. There is a subtler route to the same outcome, and it does not involve ultraviolet at all. Repeated flaring drives the formation of nitrogen oxides in a modeled Earth-like atmosphere, and those compounds absorb visible light efficiently. A planet subjected to this regime can end up wrapped in a haze that both destroys its ozone and dims the sunlight reaching its surface, cooling the ground substantially over time. The atmosphere is not stripped away in that scenario. It is chemically rewritten into something that shuts out the light the planet needed in the first place. It would be easy to end there, and it would not be honest. So the counterweight, stated plainly, none of this constitutes proof of sterility. It constitutes a difficult environment, which is a different thing. A sufficiently dense atmosphere can absorb ultraviolet on its own without needing an ozone layer. A strong intrinsic magnetic field can hold off a stellar wind, though the required strength sits at the high end of what a small, slowly rotating world is likely to generate. Volcanism can resupply an atmosphere that keeps being eroded. A planet that began with a very large water inventory can afford to lose a great deal of it and still have oceans. There is even an argument that runs the other way entirely. The ultraviolet light from these flares is a plausible energy source for some of the chemical pathways that may be needed to get life started in the first place. A star that is too quiet may present a different problem, which is that nothing ever gets going. The verdict on all of this is genuinely open, and anyone who tells you otherwise is ahead of the evidence. What can be said without hedging is narrower and stranger. The nearest star to the Earth, the one nobody has ever seen, is a star that erupts violently several times a year, and the only region around it where liquid water could exist is the region closest to those eruptions. The two facts are not independent. The zone is close because the star is faint, and the eruptions are devastating because the zone is close. Faintness and violence are bound together, and there is, in fact, a world sitting inside that zone. Part 5. The world that cannot turn. A world of roughly Earth's mass circles the nearest star once every 11 days. That sentence would have been science fiction within living memory. It is now a measured fact, and the measurement is worth understanding, because it is the technique that produced most of what this survey knows about worlds around nearby stars. The planet does not orbit the star. The two of them orbit their common center of mass, which means the star itself traces out a small circle in response to the planet's pull. Seen from here, that motion carries the star fractionally toward us and then fractionally away, over and over, on the planet's orbital period. Motion toward us compresses the wavelengths of the star's light very slightly. Motion away stretches them. Measure that shift precisely enough, watch it repeat, and the planet declares itself without ever being seen. The precision required is the remarkable part. The stellar motion being detected here corresponds to a speed of 1 meter or 2 per second. That is walking pace. Astronomers are measuring a star 4¼ light-years away and determining that it is ambling toward us at the speed of an unhurried walk, and then that it has turned around and is ambling away again. The world that motion reveals sits at about 5/100ths of an astronomical unit from its star. That is roughly a 20th of the Earth's distance from the Sun. It is a punishingly tight orbit by the standards of our own system, and yet, because the star is so faint, it places the planet squarely inside the range where liquid water could, in principle, survive on a surface. Its equilibrium temperature, before any atmospheric warming is accounted for, sits somewhere near 230 Kelvin. Cold, but within reach of a modest greenhouse effect. There is a second world in the system, closer in, at about a quarter of Earth's mass, with a period near 5 days. It is among the lightest planets ever detected anywhere by any method, and detecting it required reading a stellar wobble of a few tens of centimeters per second. A third and more distant candidate has been proposed and remains unconfirmed, and this survey will say so, rather than round it up into a certainty. A good deal of what follows in later parts turns on how often that rounding up has happened and what it has cost. One caveat belongs with every mass quoted in this survey, and it is easiest to state here. The wobble method measures only the component of the star's motion along our line of sight. If the planet's orbit is tilted relative to us, part of the star's true motion is sideways and therefore invisible, and the mass we calculate comes out too low. What this technique delivers is a minimum mass, not a mass. The world at 11 days is at least Earth's mass. Depending on how the system is oriented, it could be considerably heavier, and there is no way to settle the question without a second, independent measurement that this system has not yet provided. Now the question that matters. What would it actually be like there? The dominant fact is that the planet almost certainly does not turn. At 5/100ths of an astronomical unit, the tidal forces from the star are severe, and the timescale for them to slow a rocky planet's rotation to a stop relative to its orbit is short. Well under 1,000,000 years against a system age measured in billions. Whatever spin the planet was born with was taken from it during a period that, on the system's clock, was essentially instantaneous. The result is a world with one face turned permanently toward its star and one face turned permanently away. It is worth being precise about what that means, because it is genuinely difficult to picture. There is no day and no night in the sense anyone has experience of. There is a region of permanent day, where the star hangs at a fixed point in the sky and never moves from it. Directly beneath that point, the star sits at the zenith, unmoving, forever. Shadows there do not lengthen or shorten. They have been the same length for billions of years and will be the same length for billions more. Move outward from that point, and the star sinks gradually toward the horizon, still without moving. At the ring where it touches the horizon, the star neither rises nor sets. It sits there permanently, a fixed red thing on the edge of the world, casting a light that has not changed angle since the planet formed. Cross that ring and the star is gone entirely, and behind it lies a hemisphere that has been in darkness since the beginning and will remain so until the end. That night side is where the danger sits, and it is not the cold in itself. It is what the cold does to the air. If the atmosphere is thin, the night side becomes cold enough for its own gases to condense and freeze onto the ground. Once that begins, it does not stop, because the frozen atmosphere accumulates in the coldest place available, which is precisely where it fell. The day side loses its air to the night side permanently, and the whole planet ends up with a thin residue and a frozen deposit that will never sublimate. It is an irreversible failure, and it is the standard fate of a thin atmosphere world in this configuration. The escape from that trap is circulation. A dense enough atmosphere moves heat from the day side to the night side faster than the night side can freeze it out. The required density is not extreme, and models suggest that something comparable to Earth's atmospheric pressure would be sufficient. But it has to be there in the first place, and Part 4 laid out at length the several mechanisms by which this particular star spends billions of years trying to take it away. There is a gentler possibility that should not be skipped. Tidal locking into a one-to-one state is the most common outcome, but it is not the only one. If the orbit is even slightly elliptical, a planet can settle instead into a spin-orbit resonance, turning some whole number of times for every 2 orbits. The innermost planet of our own system does exactly this, rotating 3 times for every 2 circuits of the Sun. A world in that state does have days and nights, though they are strange ones, very long and unevenly heated. That option remains open here, and it would change the picture considerably. If the planet is locked, the region worth thinking about is the ring between the 2 hemispheres. It is a band of permanent twilight, wrapped all the way around the world, where the star sits low and unmoving on the horizon, and the temperature falls between the extremes on either side. Anything that endures on such a world endures there, along that seam, in a light that never changes and never will. There is a specific configuration worth naming, because it is what a locked ocean world would probably look like. Beneath the point where the star stands at the zenith, the surface is warm enough for open water. Move outward from there, and the temperature falls until the ocean freezes. The result is a single circular sea of open water directly under the star, surrounded in every direction by ice that thickens with distance from that center, out to a night side that is frozen solid. From above, it would resemble nothing so much as a single pale disk set into a white sphere, and it is one of the more plausible surface arrangements for a temperate planet in this part of the census. The reason to take all of this seriously, rather than treating it as an exotic special case, is a matter of numbers. Statistical work on planet occurrence rates suggests something close to 1 temperate, roughly Earth-sized planet per red star, on average. There are hundreds of billions of red stars in this galaxy. That implies tens of billions of worlds in configurations broadly like this one, and it implies several of them inside our own local census of 60. The arrangement described in this part is not the strange exception. It is very likely the most common kind of temperate surface in the galaxy, and the Earth is the outlier. There is one further energy source that a locked planet at that distance would have. Tidal flexing does not only stop a planet's rotation, it also heats the interior. If the orbit retains any eccentricity, the planet is being kneaded continuously, and that kneading warms the rock from within. In our own system, the same process drives the most volcanically active body we know of. On a world whose atmosphere is being steadily stripped, volcanism is not a hazard. It is a resupply mechanism, and it may be the only one available. Finally, the honest limitation. Nothing in this description has been observed. Not the atmosphere, not the surface, not the rotation state. The planets of the nearest star do not transit from our line of sight, which means the light of the star never passes through the planet's air on its way to us, which means the single most powerful technique for reading an atmosphere is unavailable here. Everything above is inference built on mass, distance, and physics. It is good inference. It is not observation. What can be said with confidence is smaller and stranger than the artist's impressions suggest. The nearest potentially temperate world to the Earth is a place where the sun does not move, where half the surface has never seen light and the other half has never seen dark, and where the only plausibly livable ground is a ring of endless evening around a planet that cannot turn. It is not another Earth. It is something our language was not built to describe. Part 6. The two that look like home. Standing beside that faint red star, in the same system, are the two brightest members of the entire local census. The first is a yellow star, very slightly larger and more luminous than our own, about 10% heavier and about half again as bright. The second is an orange star, somewhat smaller and cooler, carrying about 9/10 of the Sun's mass and radiating about half its light. They orbit one another on a stretched ellipse, swinging between roughly 11 and 36 astronomical units apart, completing one circuit in about 80 years. That is a separation that runs from about the distance of the outermost gas giant in our system down to inside the orbit of the ringed planet, and it changes visibly across a human lifetime. Seen from Earth, they are not separable by eye. They merge into a single point that ranks among the three brightest stars in the night sky, though only observers in the southern half of the world ever see it. These two are the nearest stars that genuinely resemble the Sun. Not approximately. Not in the loose sense in which any yellow star resembles any other. In mass, in temperature, in age, and in composition, they are close analogues, and there is nothing else like them within a considerable distance. That fact carries more weight than it first appears to, and it is worth stating as a ratio. Out of roughly 60 neighbours, essentially 2 are close matches for our own star. That is about 3%. Widen the definition to include everything broadly Sun-like, and the figure rises to something like 7%, which happens to match the proportion of Sun-like stars in the galaxy as a whole. The local sample is not unlucky. It is representative. Stars like ours are simply not common, and the neighbourhood reflects that faithfully. The pair are slightly older than the Sun, by perhaps 1 billion years, and somewhat richer in heavy elements. That second point cuts in a hopeful direction. Heavier elements are the raw material of rock, and a system that formed from enriched gas has more of it available. On most models, that makes rocky planets there more likely rather than less. There is a structural problem with planets in a system like this one, and it constrains where they can be. Two stars, swinging between 11 and 36 astronomical units apart, create a gravitational environment with 3 distinct regions. Close in around either star, orbits are stable because the near star's gravity dominates completely, and the far one is a distant perturbation. Far outside both, orbits are also stable because at sufficient distance, the pair behaves as a single mass. Between those two regions lies a wide band where nothing survives, because a planet there is pulled hard by both stars in turn and is eventually ejected or destroyed. The temperate zone around each of these two stars falls comfortably within the inner stable region, which is why the system has remained a serious target for planet searches through decades of disappointment. There is also something worth noting about the view in the other direction. From a planet in that system, our own Sun would be a perfectly ordinary naked-eye star, of moderate brightness, sitting in a constellation that would look almost exactly as it does from here, because 4 light-years is not far enough to rearrange the distant background stars. Anyone there with the equivalent of an unaided eye would see our star without difficulty, and would have no particular reason to single it out from the several thousand others in their sky. The relationship runs both ways, and it is not symmetrical in the way one might assume. They could see us. We cannot see the nearest member of their own system. Whether any such planets exist is a question this survey will not settle tonight, and it does not need to, because it has already been given a full night of its own. What can be said is that the search has been long and the results have been humbling. A giant planet candidate has been detected around the brighter of the two, using the largest telescope ever placed in space. It appeared in one observing session and was absent from a later one, swallowed back into the glare of its own star. It remains a candidate and nothing more. And an earlier claimed planet around the cooler of the two, announced with some confidence, was withdrawn after reanalysis showed the signal was an artifact of the observing schedule rather than anything orbiting anything. That is the second retraction this survey has touched, and it will not be the last. The pattern is becoming a theme, and it is worth naming now so that it is recognizable later. The nearest stars are the ones we watch most closely, with the newest instruments, in the greatest hope. That combination produces genuine discoveries. It also produces a long history of things that were announced, believed, painted, and then quietly taken apart. There is a reason the nearest stars are disproportionately represented in that history of withdrawals, and it is not carelessness. A signal from a nearby star is stronger, so smaller effects become detectable, and smaller effects are exactly the ones that can be produced by the star itself rather than by anything orbiting it. Magnetic activity, surface convection, and rotation all leave traces in the same measurements that reveal planets, and on a well-studied nearby star, those traces are visible where on a distant star they would be lost in noise. Being close to us does not make a star easier to read. In several important respects, it makes it harder because it exposes every small thing the star does. The two brightest members of the local census are, in the end, an unfinished question. Two suns much like our own, 4¼ light-years away, orbiting each other on a slow ellipse, with a faint, violent companion drifting far out on its own enormous orbit around both. What waits there, if anything does, deserves more time than this survey can give it. So we leave that system where it stands and turn outward, and this is a reasonable place to gather up what the outward turn has produced so far. 60 stars within 17 light-years. 9 of them available to the unaided eye. The ruler for all of it, built out of 8 light minutes to our own star, and then abandoned entirely, because every other distance in the subject has to be measured in years of light instead. The first honest measurement of one of those distances took a man over a year of consecutive nights, and it was made on a dim star, chosen not for its brightness, but because it moved. The nearest star in existence is a small red thing about 100 times too faint for human vision, burning so slowly it will still be burning in 4 trillion years, churning from core to surface and throwing out flares that briefly raise its ultraviolet output by a factor of 14,000. Inside its narrow temperate zone, there is a world of roughly Earth's mass that almost certainly cannot turn, with one hemisphere in permanent light, one in permanent dark, and a ring of unchanging twilight between them. And beside it, 2 stars that look very much like home, already visited. That is the near end of the census. Everything from here outward is stranger. There is a star that has produced 3 separate sets of planets over the last 60 years, 2 of which turned out not to exist. There is a star that no eye and no instrument could find at all until photographic plates made it possible, and whose entire class of object is invisible from every point in the sky. There are 2 objects that reached for fusion, fell short, and have been cooling in the dark ever since, and which were completely unknown until roughly a dozen years ago, despite being the 3rd nearest system to the Sun. And there is one perfectly ordinary star, the brightest in our night sky, with a body laid out cold beside it. The census gets colder as it goes outward. It also, in 1 or 2 places, gets warmer, and those places will be worth waiting for. Part 7. The star where the planets kept dissolving. At just under 6 light-years, there is a red star that has been the site of more disappointment than any other object in the local census. It carries about 16% of the Sun's mass. Its surface sits near 3,200 Kelvin. It shines at about magnitude 9.5, which places it comfortably beyond human sight, but well within reach of a modest telescope. And it is old. The estimates run from 7 to 12 billion years, which means that at the low end it is well over half again the Sun's age, and at the high end it is nearly as old as the galaxy itself. It was already ancient when our own star ignited out of a collapsing cloud. Its composition supports that reading. It is poor in heavy elements, which is the signature of a star formed early, before generations of supernovae had enriched the gas. And its motion through the galaxy marks it as an outsider to the disk we live in. It is not traveling with the local crowd. It is passing through. That motion is its most famous property. This star has the fastest apparent movement across the sky of any star known, anywhere. It shifts about 10 arcseconds every year. That sounds negligible until it is compounded. Over 180 years, it traverses an angle equal to the apparent width of the full moon. On the timescales of astronomical record-keeping, it is sprinting. That is how it was found, roughly a century ago. Not by its light, which is unremarkable, but because it refused to stay in the same place between photographic plates taken years apart. The technique that found it is the same one that has produced most of this census, and the principle behind it is simple. Nearby things appear to move, distant things do not, so anything moving quickly is probably close. It is also approaching. Its motion along our line of sight brings it toward us at over 100 kilometers per second, and it is one of the largest such velocities measured for any nearby star. In roughly 11,800 years, it will make its closest approach, passing at about 3 3/4 light years. At that moment, it will become the nearest star to the Earth, displacing the current holder of that title, before sliding on past and receding into the dark behind us. And here is the point at which this survey's central argument becomes almost unbearable in its consistency. Bringing that star inside 4 light years does not make it visible. At closest approach, it will reach roughly magnitude 8.5, still well below the naked eye floor. 12,000 years from now, when this star is the nearest object in the sky, whoever is here will look up and not see it. The nearest star of the future is invisible for exactly the same reason as the nearest star of the present. What has happened around that star over the last 60 years is a story in 4 movements, and it is worth telling in order, slowly, because it is the most human sequence in the entire census. The first movement came about 60 years ago. An astronomer working with decades of accumulated photographic plates reported a wobble in the star's position, a slow side-to-side deviation from its otherwise straight sprint across the sky. He interpreted it as the gravitational tug of planets, and he announced 2 of them, both roughly the mass of the largest planet in our own system. The result was accepted widely and for a long time. It appeared in textbooks. It was, for a period, the best evidence anyone had that planets existed anywhere outside our own system at all. It was not real. The wobble was traced eventually to the telescope. The instrument's optics had been altered partway through the observing program, and every measurement made afterwards carried a systematic shift that had nothing to do with the sky. The planets dissolved. What had been detected was the observatory. The second movement came within the last decade, and it used an entirely different and far more rigorous method. A super-Earth was announced, several times the mass of our planet, on an orbit of roughly 230 days. It was derived from radial velocity data, the same wobble in the spectrum technique that found the worlds of the nearest star, and it was announced with appropriate care by a large collaboration. It stood in the catalogues for about 3 years. Then reanalysis showed that the signal's period matched a harmonic of the star's own rotation. The star turns roughly once every 140 days, extremely slowly, as an old star should. Magnetic features on its surface rotating in and out of view produce a periodic signal in exactly the same measurements a planet does. What had been detected, this time, was the star's own breathing. Twice now, careful people looking at the second nearest star had found what they were hoping to find. Twice, what they had found was themselves. The third movement is the one that finally held. Using a spectrograph capable of measuring a star's motion to a precision of a few tens of centimeters per second, calibrated against a laser reference, astronomers detected a genuine world. It is about half the mass of Venus, and it completes an orbit every 3 days. Far too close and far too hot for anything to survive on it, but real and confirmed after a full century of searching. The scale of that measurement deserves a moment on its own, because it is one of the more extraordinary things human beings have managed to do. A planet half the mass of Venus, orbiting a star 6 light-years away, pulls that star back and forth by about half a meter per second. That is slower than a person shuffling. To register it, the instrument disperses the star's light into a spectrum and measures the positions of thousands of absorption lines against a reference produced by a laser comb, a source that emits at a set of frequencies known to extraordinary precision. The star's light is then compared against that comb night after night for years. What emerges is a curve, and inside the curve is a planet. The fourth movement followed within months. 3 more worlds were confirmed, alongside the first, all between roughly a fifth and a third of Earth's mass, with periods running from a little over 2 days to under 7. These are the lowest mass planets ever detected by the radial velocity method anywhere in the sky. 4 real worlds, at a star that had produced nothing but ghosts for 60 years. And now the arithmetic that closes the story. All 4 of them orbit within about 3/100ths of an astronomical unit. Every single one lies inside the inner edge of the habitable zone, and not marginally. Their equilibrium temperatures run from roughly 300 to 400 Kelvin. Recent modeling of the 4 concludes that they are volatile poor, which is the technical way of saying dry. Rocky, small, hot, and without meaningful atmospheres. 4 planets, after a century of false starts, and not one of them a place where anything could hold on. There is a plausible reason for their dryness, and it connects back to the star's age. A star formed that early, out of gas that had not yet been enriched by many generations of supernovae, has less rock and less ice available in the disk that surrounds it. Small, dry worlds are what such a disk would be expected to produce. The planets are poor because the star is old, and the star is old because it formed before the galaxy had made much of anything. Its age has not made it safe either, which is a finding that complicated a comfortable assumption. Old red stars were expected to have spun down into magnetic quiet. This one has been caught flaring. Whatever calm comes with age, it is not complete. It is worth picturing what those 4 worlds actually experience, since they are among the closest planets to Earth that will ever be studied. From the surface of the innermost, the star would fill a substantial part of the sky, a deep red disk, many times the apparent width of the Sun, as seen from here, sitting motionless, because these worlds too are certainly locked. The light would be dim by our standards, and heavily weighted toward the infrared, so the ground would be warm, while the sky looked dark and dull red. There would be no seasons, no sunrise, and no weather in any sense that requires an atmosphere, because there is very probably no atmosphere left to have any. This star is also, by some measures, among the most heavily observed objects in the sky, and that is a direct consequence of its position. It is close, it is quiet, it is faint enough to be studied without saturating a detector, and its motion makes it easy to identify. Every new generation of instruments has been pointed at it as a test case. That is precisely why its false positives were so public. A star that everyone examines with every new tool is a star whose errors are made in front of an audience. What this star leaves behind is not really an astronomical lesson. It is an epistemological one. 3 separate times, over 60 years, competent people using the best available instruments looked at the second nearest star in the sky and reported worlds that were not there. Each time the error came from somewhere different, and each time it was found by someone checking. The neighborhood has been extremely difficult to read, and every genuine result in this survey sits on top of a considerable pile of corrections. Part 8. The reason. At just under 8 light-years, there is a red star that carries about 9% of the Sun's mass. That places it very near the minimum required for a star to burn hydrogen at all. Its surface sits under 3000 Kelvin, cooler than the filament of an old incandescent bulb, and it shines at about magnitude 13.5. Magnitude 13.5 is roughly 300 times fainter than the naked eye limit. No human being has ever seen this star. No human being ever will. It was pulled out of the dark from photographic plates, identified by its motion across the sky rather than by anything about its light, which is the same technique that found the second nearest star, applied to an object 4 times fainter. It is young by the standards of its class, rotating quickly and flaring heavily. 2 candidate planets were announced there, and both remain disputed. It has no confirmed worlds. It is, in almost every respect, an unremarkable object. And that is exactly why it matters, because this survey has now reached the point where the central question can finally be answered properly. Roughly 3 out of every 4 stars in this galaxy are red stars of this general kind. Some estimates put the fraction as high as 3/4 and some slightly lower, but the figure is not seriously in dispute. They are the overwhelming majority of everything that burns. And there is not one red star anywhere in the entire sky bright enough to be seen without a telescope. Not one. Not the nearest, not the largest, not the closest to the limit. There is a single borderline case, a red star at about 12.5 light-years that hovers around magnitude 6.5, which under exceptional conditions from an exceptional site might just be picked out by an exceptional eye. Everything else in the most populous category of object in the universe is beyond human vision permanently. Sit with what that means before moving on. The most common kind of star that exists is a kind of star that no person has ever seen, in any direction, at any distance, on any night in the history of the species. Not because they are hidden behind anything, not because they are far away, because of what they are. The reason is a number called absolute magnitude, and it is the whole mechanism. Absolute magnitude is simply the brightness a star would show if it were placed at a standard distance of about 32.5 light-years. It strips distance out of the comparison and leaves only the star's actual output. Once you have it, everything that has seemed arbitrary in this survey resolves into arithmetic. A typical red star has an absolute magnitude somewhere around 15. Run the calculation backwards and ask how close such a star would have to be for a human eye to register it, and the answer comes out at about 1/3 of a light-year. Nothing has ever been that close. The nearest star in existence sits at 4.25 light-years, which is more than 10 times too far, and it is as close as anything has ever come. So, the invisibility of the red stars is not a matter of bad luck or bad placement. There is no arrangement of the galaxy in which they would have been visible. To see one, it would have to be inside the comet shell of our own system. Now run the same calculation on our own star, because this is where it becomes personal. The Sun's absolute magnitude is about 4.8. That means the Sun would remain visible to an unaided eye out to about 56 light-years, and no further. Beyond that boundary, our star is simply not in anybody's sky. It is not faint there. It is absent. 56 light-years sounds like a considerable distance until it is compared against anything. The galaxy is about 100,000 light-years across. The sphere in which our Sun is visible to the naked eye is a bubble containing on the order of a few thousand stars out of several hundred billion. To more than 99.999% of this galaxy, our Sun does not exist as a visible object. And now, run it a third time, on one of the brightest stars in the northern summer sky. A blue-white supergiant, absolute magnitude around -8, which is to say, something on the order of 100,000 times the Sun's output. It remains visible to the naked eye across roughly 25,000 light-years, which is about a quarter of the galaxy's diameter. It is more than 2,000 light-years away, and it is one of the most prominent objects in the sky. Put those three results side by side, and the mechanism is complete. Brightness in the sky is the product of two things: how much light a star actually emits, and how far away it is. Distance dims a star according to an inverse square, so the range from 4 light-years to 4,000 produces a factor of 1,000,000. That is a large effect. But stellar luminosity varies across a range of more than 100 million to 1, from the faintest red stars to the most luminous supergiants. The luminosity term is 100 times larger than the distance term across the entire volume anyone can see, which means the sky is sorted by luminosity, almost exclusively, and by distance hardly at all. That is the answer. That is the reason. The night sky is not a map of what is near us. It is a map of what is bright, and the two are very nearly disjoint sets. Of the roughly 5,000 stars visible from a dark site, the great majority are enormous, luminous, and hundreds or thousands of light-years away. Our actual neighbours are small, dim, and almost entirely absent from the picture. Every constellation ever drawn is made of strangers. Every star used for navigation, every star given a name in every language, every star that has anchored a calendar or a myth or a season, was selected by a filter that specifically excludes the nearby. The sky we inherited is a catalogue of the rare and the far away, assembled by an instrument that could not do otherwise. It is worth asking whether a better eye would have rescued any of this, and the answer is no, by a wide margin. The magnitude scale is logarithmic, and it runs backwards, so larger numbers mean fainter objects. Each step of one magnitude is a factor of about 2.5 in brightness, and 5 steps make a factor of exactly 100. The naked eye limit of magnitude 6 is not set by the eye alone, but by the contrast between a point of light and the background glow of the sky itself. From above the atmosphere, with no scattered light at all, an unaided human eye might reach roughly 1 magnitude fainter. That improvement would change almost nothing. The gap between magnitude 6 and the nearest star's magnitude 11 is a factor of 100. The gap between magnitude 6 and the star described at the start of this part is a factor of nearly 1,000. Gaining a single magnitude closes none of it. The eye is not slightly short of the mark. It is short by 2 to 3 orders of magnitude, and no plausible biological improvement would have made the difference. It is worth imagining, briefly, what would have happened if it had. An eye that reached magnitude 15 would see a sky transformed beyond recognition. The familiar bright stars would still be there, but they would be swamped, buried in a dense scatter of faint red points, filling every part of the sky in enormous numbers. The constellations would be unfindable, because the patterns depend entirely on the bright ones standing alone against emptiness. Navigation by star would have been very much harder, and possibly would never have developed. The sky that human culture was built on is a sky made legible by our own limitations. There is a consolation in this, and it is not a small one. The invisibility is a property of our eyes, not of the sky. Nothing is missing. The 50 stars are all there, exactly where they have always been, radiating steadily in the infrared and doing nothing whatsoever to conceal themselves. We were simply built with a detector tuned to a narrow band, with a floor set in an inconvenient place, and everything below that floor went unrecorded for the entire history of our species until instruments arrived that could see past it. And the arrangement is entirely reciprocal, which is the last turn worth taking here. Hundreds of billions of red stars fill this galaxy, and every one of them has a sky. In almost every one of those skies, our sun is also invisible. We are not uniquely blind, and we are not uniquely hidden. Every star in the galaxy is standing in a crowd it cannot see, being unseen by nearly all of it. Part 9. The four that are already dead. At about 8.5 light-years, there is a hot white star of roughly twice the sun's mass, radiating about 25 times as much light, with a surface near 10,000 Kelvin. It is the brightest star in the night sky of the Earth, by a comfortable margin, and it is visible from very nearly everywhere on the planet. This is the one member of the local census that everyone has seen. It has been used to mark the turning of seasons and to time the flooding of rivers. It has been named in every language that has ever named stars. Ships were steered by it. It appears in the earliest astronomical records that survive, and it will be visible from here for as long as there is anyone to look. It is also carrying a body. Circling that star, on an orbit taking about 50 years and swinging between roughly 8 and 31 astronomical units, is a white dwarf. It holds about 1 solar mass inside a sphere slightly smaller than the Earth. It shines at magnitude 8.5, which is about 10,000 times fainter than its companion, and its proximity to that overwhelming glare makes it one of the more difficult objects in the sky to observe, despite being one of the nearest. Its existence was known before anyone saw it, and the way that happened is one of the finest pieces of reasoning in the subject. The bright star was observed, over decades, to sway. Against the background of the sky, it did not move in a straight line, as a star with simple proper motion should. It wove. Something was pulling on it periodically, something with substantial mass, and nothing was visible in the vicinity that could account for it. From the wobble alone, an unseen companion was predicted, along with a rough estimate of its mass and period. The prediction came with a sentence that could stand as the thesis of this entire survey, written down long before there was any way to verify it. The existence of countless visible stars, it was argued, can prove nothing whatsoever against the existence of countless invisible ones. That is the claim this survey has spent 8 parts demonstrating, and it was made from a wobble. The man who made it died without ever seeing the object he had predicted. It was found roughly 2 decades later, and not by anyone looking for it. A lens maker was testing a new refracting telescope, its main lens some 18.5 inches across, and turned it toward the bright star to see how the instrument handled a difficult target. Beside the star, huddled close in the glare, there was a faint pinpoint of light. It was the companion, exactly where it had been predicted to be. It was also the first white dwarf that human beings had ever seen, though it would be more than half a century before anyone understood what they were looking at. What they were looking at was a corpse. The object was once the dominant member of that system, a star of perhaps 5 times the Sun's mass, burning far more brightly and far more quickly than its companion. It ran through its fuel, swelled, shed its outer layers into space, and collapsed onto its own exposed core. It stopped shining as a living star, something on the order of 100 million years ago. The system as a whole is only a few 100 million years old, which is how a star of twice the Sun's mass can be paired with an already dead companion. The dead one was originally the heavier of the two, and heavier stars finish first. What remains is difficult to hold in the head. Roughly the mass of our Sun, compressed into a volume slightly smaller than this planet. A cubic centimeter of it weighs upwards of a ton. A teaspoon of the material would weigh about as much as a small car. Nothing is burning inside it. There is no fusion, no energy source, nothing generating heat at all. What holds it up against its own enormous gravity is not pressure from heat, but a quantum mechanical refusal. Electrons cannot be forced into identical states, and when matter is compressed hard enough, they resist further compression on that basis alone, regardless of temperature. The entire star is supported by a rule about how electrons may be arranged. It is a body held together by a prohibition rather than by a fire. That prohibition has a ceiling. Above about 1 4/10 solar masses, gravity overwhelms it, the electrons lose, and the collapse continues into something considerably denser. Every white dwarf in the universe sits below that line, which is why they are all in roughly the same size range, regardless of what they started as. The surface of this one is still near 25,000 Kelvin, more than 4 times hotter than the Sun's, which is why it is white rather than red. But that heat is stored, not produced. It is the residual warmth of the collapse, radiating slowly away into space, with nothing replenishing it. The object is cooling, and it will keep cooling for trillions of years, dimming and reddening as it goes, until it is a cold, dark cinder, radiating nothing at all. Not one such cinder exists anywhere yet. The universe is nowhere near old enough. Every white dwarf that has ever formed is still glowing, and will be for an era of the universe that has not yet begun. Because that cooling proceeds along tracks that are well understood, the temperature of a white dwarf functions as a clock. Measure how cool it has become, and you can estimate how long it has been dead. Applied across a population, this gives one of the more elegant results in astronomy. The coolest white dwarfs found anywhere set a minimum age for the disk of the galaxy, because the galaxy must be at least as old as the time required for its oldest corpses to have cooled that far. There is a stranger property that some of these objects show, and it is worth pausing on. A white dwarf's gravity is so intense that heavy elements sink out of its atmosphere and disappear from view within a matter of days. Any heavy element detected at the surface must therefore have arrived recently. And yet a substantial fraction of white dwarfs show exactly that: iron, magnesium, silicon, calcium, sitting in atmospheres that should have been swept clean almost immediately. The material is falling in continuously, and the composition of what falls in matches the composition of rocky planets. These are stars consuming the debris of their own destroyed worlds, and the chemistry of the meal can be read directly off the surface. The companion in this system has left its own mark on the star it orbits. When it swelled and shed its outer layers, some of that material would have fallen onto the bright star beside it, and the bright star's surface composition carries an anomaly that has been read as exactly that. The living star is wearing a thin layer of its dead partner. Now the part that changes the shape of the census. That object is not alone in this. Within 17 light-years, there are 4 white dwarfs. 4 collapsed remains of stars that finished burning long ago, sitting quietly in the local volume among the 60. The second orbits a bright northern star at about 11.5 light-years, and it was found the same way as the first, predicted from a wobble before anyone saw it. The other 2 are solitary, at about 14 and 15 light-years, with no living companion and no particular reason for anyone to have noticed them. All 4 are far below naked eye reach. There is a symmetry worth noticing in how the first 2 were found. Both were predicted from the wobble of a bright companion before anyone laid eyes on them, and both turned out to be exactly what the wobble said they should be. The 2 nearest stellar corpses to the Earth announced themselves not by emitting anything, but by pulling on something that did. That is the same principle that finds planets, applied 1 rung up the mass ladder, and it remains one of the few ways to detect an object that gives off almost no light at all. Set that against the 9 stars a person can actually see, and the arithmetic comes out cold. 4 corpses among 60 neighbours. Roughly 1 dead star for every 2 living stars anyone will ever pick out from their own back garden. That ratio is not a local accident. Something like 97% of all stars, including our own, will end this way. White dwarfs are not an exotic outcome. They are the standard one, the ordinary conclusion for almost everything that burns. A galaxy that has been making stars for 12 billion years has accumulated an enormous population of them, and the local sample reflects that faithfully. The bright star will join them. In something on the order of 1 billion years, it will exhaust its own fuel, swell, shed its outer layers, and collapse. At that point, the system will contain 2 white dwarfs orbiting one another in the dark, and nothing living at all. The brightest star in Earth's night sky has a finite tenure, and it is already using it up faster than our own sun is. Part 10. The ones that never caught. The third nearest system to the sun sits at about 6.5 light-years, and until roughly a dozen years ago, nobody on Earth knew it was there. That sentence should be read twice. Not the 300th nearest system, not something on the far edge of the local volume. The third. Closer than the brightest star in our sky, closer than every object catalogued in this survey except 2, and it was entirely absent from human knowledge until within the last 15 years. Its 2 members are not stars. They never managed it. The dividing line for becoming a star is about 7.5 to 8% of the Sun's mass, roughly 80 times the mass of the largest planet in our own system. Above that threshold, the core becomes hot enough and dense enough for hydrogen fusion to become self-sustaining, and the object settles into a long, stable life. Below it, the core never quite reaches those conditions. The object contracts, heats up on gravitational collapse alone, glows for a while on that borrowed warmth, and then simply cools forever, with nothing to replace what it radiates away. Between roughly 13 and 80 times that giant planet's mass, there is a middle case. Such an object can fuse deuterium, a heavier form of hydrogen with an extra neutron, which ignites at a lower temperature than ordinary hydrogen. But deuterium is scarce, making up a tiny fraction of the available material, and the burn is correspondingly brief and thin. It flickers for a few million years and then goes out, and the cooling resumes. These objects are called brown dwarfs, and the 2 at 6.5 light-years are a matched pair. They carry roughly 34 and 28 times the mass of our system's largest planet, and their surfaces sit near 1,300 and 1,200 Kelvin. That is cooler than a candle flame. They radiate almost entirely in the infrared, and their visible output is so negligible that no optical survey would ever have registered them. They were found in an infrared survey, by their motion, which is the only way they could have been found. They orbit one another at about 3.5 astronomical units, with a period near 27 years. And they have weather. Seen from close range, neither would look like a star. They would look like enormous dim embers, glowing a deep sullen red shading toward magenta, bright enough to read by only if you were very near, and giving off most of their output as heat you would feel rather than light you could see. Their brightness varies as they rotate, and the variation follows a pattern consistent with patchy cloud cover, rotating in and out of view. The clouds are not water. At those temperatures, the condensates are iron and silicate minerals. These are clouds of rock and metal, forming, drifting, and raining out in an atmosphere hot enough to keep them suspended. A crude map of those cloud patterns has been assembled from the way the light varies, which makes this pair the first objects outside our own system to have anything resembling a weather map drawn for them. Wind speeds on the order of 600 meters per second have been inferred from the mismatch between the rotation of their atmospheres and the rotation of their interiors. There is a reason this particular pair has received so much attention, and it has to do with where they sit in the sequence of cooling. Brown dwarfs are classified by temperature into a series of spectral types, and the two members of this pair straddle the boundary between two of them. That boundary is thought to be exactly where the mineral clouds break up and rain out of the atmosphere, clearing the way for light from deeper layers to escape. Having two objects on either side of that transition, at a known common distance, formed at the same time out of the same material, is about as close to a controlled experiment as this subject ever gets. Their atmospheres are chemically rich, in a way stars are not. Warm brown dwarfs show water vapor and alkali metals such as sodium and potassium. Cooler ones show methane. The coldest known show ammonia, and their spectra are closer to those of giant planets than to those of stars. Somewhere along that sequence, the distinction between a failed star and a large, cold planet stops meaning very much at all. The fourth nearest object to the Sun is another one of these, solitary, at about 7.5 light-years, and it is colder still. Its surface sits near 250 Kelvin, which is below the freezing point of water. It is not merely dim. It is cold in the ordinary sense of the word. If you could somehow stand near it, you would feel no warmth from it at all. It carries clouds of water ice, and it was found the year after its neighbour, which is to say, also within the last dozen years. Take stock of what that does to the census. The third and fourth nearest objects to our own Sun are respectively a pair of failed stars wrapped in clouds of vaporized rock and a solitary object colder at its surface than an Antarctic winter. Neither existed in any catalogue, in any language, at any observatory until the last dozen years. There is a difficulty in categorizing these things that is worth sitting with rather than resolving. Above them are the smallest stars. Below them are the largest planets. There is no clean physical boundary at either end, only a set of thresholds that were chosen because they were convenient. An object of 15 times the largest planet's mass, drifting alone through the galaxy without a star, can be described accurately as a failed star or as a planet without a sun, and both descriptions are correct. The universe did not arrange itself into our categories. How many of them there are is still an open question, and the estimates have moved considerably as surveys improved. Early work suggested they might rival stars in number. Later and better surveys brought that figure down substantially. Even at the conservative end, there are billions of them in this galaxy, and every single one is invisible to the unaided eye from any distance whatsoever, because they are not merely faint invisible light. They are essentially absent from it. Their properties resist measurement in a way that stars do not. Because a brown dwarf cools continuously and never settles at a stable temperature, its mass and its age cannot be separated from one another by observation alone. A given surface temperature might belong to a heavy object that is young or a light object that is old, and the two possibilities look identical. Reading one of these objects requires additional information that is usually unavailable. It is worth noting that these two are not the only such objects in the census. At about 12 light-years there is an orange star with a pair of brown dwarfs in orbit around it, one warm and one considerably cooler, which makes that system unusually valuable. A normal star, a warm failed star, and a cold one, all at a single known distance, all formed at the same time from the same cloud. Comparisons of that kind are rare and are worth a great deal. The reason all of these objects arrived so late in the census comes down to a single technological fact. Astronomy for most of its history was conducted in visible light, first by eye and then on photographic plates, and an object that emits essentially nothing in visible wavelengths does not simply appear faint in such a survey. It does not appear at all. It is not a matter of insufficient exposure or inadequate aperture. The signal is in a different part of the spectrum entirely. Until detectors sensitive to infrared radiation became available and were pointed systematically at the whole sky, an entire category of nearby object was not merely undiscovered, but undiscoverable, and the local census was missing pieces nobody knew to look for. What can be said is what they are doing, and it is the quietest fact in this survey. They gathered themselves out of a cold cloud, contracted, warmed, reached toward the threshold, and came up short. Since then, they have been radiating away the last of the heat of their own collapse. They are still doing it. They will still be doing it long after the sun has finished burning and collapsed into a corpse of its own, cooling slowly, in the dark, 6.5 light-years from here. Part 11. The map is not finished. At about 12.5 light-years, there is a small, quiet, ancient red star. It carries about 9% of the sun's mass. Its surface sits near 3000 Kelvin, and it shines at about magnitude 15, which is roughly 1,000 times below anything a human eye can register. It is nearer to us than several stars that have been catalogued for centuries. It was not identified until a little over 20 years ago. The circumstances of its discovery are worth dwelling on because they say something about how thin the coverage of the local volume has actually been. It was not found by a survey of stars. It surfaced in archival images that had been taken for a completely different purpose, a search for moving objects much closer to home, within our own planetary system. Somebody went back through that archive looking for things that shifted between frames, and found one that was shifting far too much and in the wrong way to be anything nearby. It was a star, 12.5 light-years out, sitting in data that had been collected and set aside years earlier. Once measured, it turned out to be unusual in a way that matters for the final part of this survey. It is old, perhaps 8 billion years. It rotates slowly, and it shows very little flare activity. Among the red stars of the local census, which are as a class violent, this one is genuinely calm. It carries at least 3 planets, 2 of them close to Earth's mass, and one of those ranks by similarity measures among the most Earth-like worlds catalogued anywhere. That is a considerable amount of significance to have been sitting in an asteroid survey's discard pile. And it is not an isolated case. The brown dwarf pair described in the last part, the third nearest system to the Sun, was found roughly a dozen years ago. The solitary cold object at 7.5 light-years, fourth nearest, was found the year after that. Set those three together, and the implication is uncomfortable. Within roughly the last 20 years, the third and fourth nearest objects to the Sun were added to the list, along with a star at 12.5 light-years carrying a temperate world. The map of the immediate neighborhood was being materially redrawn, while most people listening to this were already adults. It was not being refined at the margins. Entries were being added near the top. The pace is easy to underestimate, so it is worth quantifying. Since the turn of the century, more than a dozen new systems have been added to the census within about 30 light-years of the Sun. Most of them are brown dwarfs and very faint red stars, which is exactly the population the argument of this survey would predict. But the point is the rate. This is not a trickle of marginal cases at the outer boundary. It is a steady accumulation of objects at close range that nobody had noticed. The longer arc makes the same point more sharply. 2 centuries ago, the number of stars whose distances were known was 0. A century and a half ago, it was a handful. A century ago, the local list ran to perhaps a couple of dozen, and every one of them had been found in visible light. The figure of 60 is a recent construction, assembled almost entirely from objects that visible light astronomy could never have reached, and there is no reason to treat it as final. It is simply the current state of account that has been rising steadily for as long as anyone has been keeping it. Current estimates suggest the census within about 30 light-years remains incomplete at the level of perhaps 10 to 30%. The missing objects are not distributed randomly. They cluster in 2 categories: the coldest brown dwarfs, which emit so little that only the most sensitive infrared instruments can register them at all, and faint companions, hidden in the glare of brighter stars, which are difficult for an entirely different reason. That second category deserves a word. A dim object, sitting a few arcseconds from a bright one, is not faint in absolute terms so much as overwhelmed. The problem is contrast, not sensitivity, and it requires specialized techniques to suppress the light of the primary before anything beside it becomes visible. Several of the objects in this survey were found precisely that way, and there is no particular reason to think the process is complete. Some of the 60 may turn out to be more than one thing. 2 techniques drove essentially every late discovery in this census, and they share a quality that is worth naming explicitly. The first is infrared detection. It finds objects by their heat rather than their light, which means it works on precisely the population that visible light astronomy is blind to. The second is proper motion. It finds objects by their movement across the sky, which means it selects for nearness directly, without reference to brightness at all. Neither technique looks for what is bright. One looks for what is warm, and one looks for what is moving, and both of those properties are associated with being close. That is the correction the last century has been quietly applying to a sky that, left to the eye alone, is sorted entirely the wrong way. Proper motion does have a failure mode worth mentioning for honesty's sake. A distant star traveling very fast through the galaxy can produce the same apparent drift as a nearby star traveling slowly. The method identifies candidates, it does not confirm them. Parallax remains the arbiter, and every object in this census has had its distance settled that way. There is also a category that may be genuinely beyond reach for now. Some of the missing local objects are probably free-floating bodies of planetary mass, drifting between the stars without any star of their own. Such things emit almost nothing at all. They can be found by gravitational lensing when they happen to pass in front of a more distant star, which is a matter of luck and cannot be arranged, or by direct imaging at very close range, which requires knowing where to point. There may be a considerable number of them within a few light years, and there is currently no reliable way to establish the figure. The conclusion this part is driving toward is straightforward and slightly unsettling. The map of the immediate neighborhood is not finished. It was assumed complete more than once, and each time the assumption turned out to be wrong by several entries. New objects are still being added at close range. Anyone who has looked up at a clear night sky and felt they were seeing a settled, fully catalogued arrangement was mistaken by a margin that is difficult to overstate. Whether the count can be closed at all is a live question. Infrared surveys have already swept the whole sky more than once, and each pass has gone deeper. The coldest class of brown dwarf was not even defined as a category until such surveys found the first examples, which means an entire type of nearby object was unknown to science within living memory and was then discovered, named, and populated within a few years. Instruments now under construction and recently commissioned are expected to push further into that range. The honest expectation is that the local census will keep gaining entries for some time, and that the entries will keep being colder, dimmer, and closer than intuition suggests. There is one small detail about that quiet, ancient star that belongs here, and it is the sort of thing that stays with you. From that star's position, the Earth passes directly in front of the Sun. The system lies inside the narrow band of the sky, from which our own planet is a transiting world. If there were anyone there with the instruments we have, they could detect the Earth by exactly the method we use on them, a tiny periodic dimming as a small dark world crosses the face of its star. We found them in a discarded archive 20 years ago. They, in principle, could have found us any time at all. Part 12. What is actually out there? After 11 parts of flares, corpses, retractions, and objects too faint to see, there is a fair question waiting. Is there anywhere in the local census where something could plausibly be living? The honest answer is that there are two reasonable candidates, and both of them have to be held very loosely. The first is at about 11 light years. A temperate world of at least 1 1/3 Earth masses circles a red star once every 10 days at the inner edge of the habitable zone. What makes it interesting is not the planet, but the star. It is old, it rotates slowly, and it is unusually inactive. Among the red stars nearby, which as a class erupt several times a year, this one is close to placid. If a red star can host a stable surface anywhere in this census, this is the most likely place for it. The second is the quiet ancient star from the last part, at 12.5 light years. It carries a world of roughly Earth's mass that scores among the highest values ever assigned on the similarity indices used to compare planets to our own. That phrase deserves to be unpacked rather than allowed to sit there sounding encouraging. The similarity index is a composite of radius, density, escape velocity, and estimated surface temperature. It is a useful shorthand for sorting a catalogue. It is not a measure of habitability, and high scores have been assigned to worlds now understood to be hostile. It tells you a planet is roughly the right size and roughly the right temperature. It tells you nothing about whether there is any air. And that is the caveat that has to be applied to all of it, without softening. A location inside the habitable zone is not the same thing as a habitable location. The zone is a line drawn on a diagram marking where liquid water could exist on a surface, if everything else went right. Almost nothing else ever goes entirely right. The boundaries are model-dependent, and conservative and optimistic definitions of the zone can differ by nearly a factor of 2 in orbital distance, which is enough to move planets in and out of it, depending on whose paper you are reading. For the world at 12.5 light years, one recent assessment puts the probability that it has retained a substantial atmosphere across its lifetime at roughly 3 chances in 100. 3 in 100 that there is any air there at all. That is the current state of the most Earth-like world in the local census. Both candidates are near certainly tidally locked. Neither transits from our line of sight, which means the light of their stars never passes through their atmospheres on the way to us, which means the single most powerful technique for detecting an atmosphere is unavailable for both. Everything anyone says about either of them is inference. So that is the state of the search, stated plainly. 2 candidates, both around red stars, both probably locked, both with unknown atmospheres, and one with a 3% chance of having one at all. And yet the instruments are catching up, and the last few years have produced something that genuinely was not possible before. At about 12 light-years, there is an orange star with a giant planet in orbit around it, and that planet has been photographed. Directly. Not inferred from a wobble, not deduced from a shadow crossing a stellar disk, but imaged as a point of light separated from its star, using the largest telescope ever placed in space. The planet is several times the mass of the largest world in our own system, orbiting at roughly 28 astronomical units, which is considerably wider than the earlier wobble-based predictions had suggested. Its temperature is near 275 Kelvin, which makes it one of the coldest worlds ever directly photographed, hovering close to the freezing point of water, rather than blazing like almost everything else that has been imaged at that range. Follow-up observations found water ice clouds in its atmosphere, along with a chemistry rich in carbon monoxide and poor in methane, which implies strong vertical mixing, dragging material upward from hotter depths faster than the chemistry can settle. Consider what that represents. Within a few years, this subject has moved from inferring the existence of nearby worlds to photographing one and reading the weather in its upper atmosphere. Not for a temperate, rocky planet, not yet. But the technique now exists, and the direction of travel is unmistakable. There is a second kind of signal that has appeared recently, and it is quieter and stranger. A red star at about 12 light-years produces a repeating pattern of radio bursts. They recur on the orbital period of its innermost small planet, which is the strongest argument that the planet is involved rather than the star acting alone. Nobody serious has suggested this is a voice, and this survey will not either. What it may be is the first indirect evidence of a magnetic field around a rocky planet outside our own system. The same physical process operates here, between the largest planet in our system and its innermost large moon, generating radio emission that would in principle be detectable across interstellar distances. And a magnetic field is not a curiosity. It is the shield that holds off a stellar wind. It is, quite possibly, the difference between a rocky world in a red star's habitable zone keeping its atmosphere and losing it. If that is what is being detected, it is the most important thing anyone has found in the local volume in a long time. Which brings this survey to its last entry, just past the edge of the region we have been calling near. At about 20 light-years, there is an unremarkable red star, and for a few years, it was the most famous address in the sky. A world was announced there of roughly 3 Earth masses, sitting squarely in the middle of the habitable zone. Not on the scorched inner edge where the 4 dry worlds of Part 7 are packed. Not out in the frozen dark. The temperate center. It was reported everywhere as the first genuinely habitable planet ever found beyond our own system. One of the people who found it thought enough of it to give it a human name. Artists painted its oceans and its rocky shores under a soft red sky. For a short while, a great many people believed the search was effectively over. Then careful follow-up work took it apart. Other groups reanalyzed the data, modeled the star's magnetic activity properly, and found that the signal attributed to the planet matched the star's own behavior. It was the same failure this survey has now documented 3 separate times. A star's surface, breathing slowly, red as a world. One of the astronomers who dismantled it said it about as flatly as such a thing can be said. The planet does not exist. Real worlds do orbit that star, and several of them are confirmed. But the one that was loved was never built. It was a shape painted with longing across an empty patch of sky, and it is worth letting that land rather than hurrying past it. It was not the only casualty at that star, either. A second claimed world was withdrawn alongside it, for the same reason, and the system's planet count has moved up and down repeatedly over the years as signals were proposed, questioned, and settled. What remains is a small set of confirmed worlds, all of them well inside the habitable zone's inner edge, all of them too hot. The temperate one was the only one anyone cared about, and it was the one that was not there. There is one more thing about that star, and it is the last fact of this survey. A message was sent to it. From a large radio dish on a peninsula by a sea, several hundred texts written by more than 500,000 people were gathered up, aimed at that dim red star, and transmitted. That signal has been crossing the dark ever since, and it is due to arrive in the late 2020s, which is not far off at all. There is a detail in that transmission worth knowing. It was aimed at a specific planet in that system, and that planet is real. It is simply far inside the inner edge of the temperate zone, and almost certainly much too hot for anything to survive on it. The message is arriving at a genuine address where nothing can live, sent because of a neighboring address that turned out not to exist. Several other deliberate transmissions have gone out from the same facility toward other nearby stars, with arrival dates spread across the coming decades and centuries, and every one of them is still in flight tonight, crossing the same dark this survey has spent 2 hours describing. It will reach a small red star, 20 light-years away, where the one world we most wanted was never real. It will arrive politely, on schedule, at a place that does not exist, and nothing will come to answer it. And still the sensor stands where it has always stood. 60 stars within 17 light-years. 9 you will ever see with your own eyes. Roughly 50 that you will not, burning steadily in the infrared in every direction around this planet, exactly as they have through every night of every year that anyone has ever looked up. 4 of them are dead. Several of them erupt. 2 of them never quite caught fire at all. And somewhere among them, wrapped in every possible caution, there may be a small, warm surface with air above it. None of it needs finding tonight. None of it is going anywhere. The neighborhood is stranger and quieter and colder than anyone standing outside and looking up has ever guessed, and it is also entirely, permanently there, whether or not a single pair of eyes is open to receive it. Let your breathing slow. Let the sky go on burning without you. Sleep well, and good night.